Hello. So it has been a while since I last recorded, and but I finally got some time recently, or right now, to continue or do what I can to make some progress. Also, I found a new thing that I want to investigate, and so I'm quite eager to figure this out. Now, first of all, there's something I forgot in the last video. I turned on a warning about missing prototypes, but I didn't actually fix the errors that that warning generated because I forgot to make clean. And so the thing is, these functions no longer have these functions that I declared, this one here, was non-static, but it didn't have a prototype for it, and so the warning was now being fired for that line. And also the input command implementation did not have a prototype for the function that it was declaring, and so but the prototype was in a header file, which I just forgot to include. And same kind of deal in input.c. It just did not include the header file for the actual function it was defining, and so it fired the missing prototype warning. So I'm just going to add this as a or amend the last change with this stuff, and we'll just oops, GCM, and we want to amend, right? Okay, that's all. And now I found, so what I want to actually investigate is I want to figure out how many well, I want to get some statistics on how often certain kana appear in normal text, more or less normal text. And I don't think I need it to be super accurate or super representative, but I do need it to kind of get a general idea of how often certain kind of characters appear. And the reason for this is I want to investigate whether or not the kana for wa, whether or not I should assign a single character to this, like w, or two, WA. Now, if it's W, then that means that a whole bunch of key sequences for kanji will not be available. So if this is just W, wa, then that means that WD or WF cannot be assigned to any kanji, which is a trade-off. And so I need, in order to figure out if that trade-off is worth it, I need to get some statistics on how often kana appear in text. Now, I already have those statistics for what's it called, for kanji, and that is available. That is in a different location. That's actually checked into the repository here in third party. Let's open this. Okay. So this is something I downloaded. I didn't generate it myself. And ooh, it's not letting me switch. The file can okay. The file contains links to other files. Should they be updated? No. And so the statistics are here. So in this data was generated with documents that total this many kanji. So this is quite a large number. Looks like it is 133 billion. And the actual distribution of each kanji are here. And so if I want to determine if a kanji so if I want to determine if I want to sacrifice 40 kanji for the purpose of making this character easier to type, I need to figure out how often this character appears in text and how often the 40 kanji appear in the text. Because W plus eval plus some other key, there's about 40 different sequences you can do. So W1, W2, W3, W4, these would all be separate kanji. We currently have about 1,250 kanji assigned, but we're using WA for wa. And so if we want to know if if it is like worthwhile to make this trade-off, we have to go to kanji with rank 12, 1250. Let's see here. 1250. This is kind of laggy. It's hard to use. 12, like around here, and up by 40. So like 1210 or so. And we need to figure out if these will appear in in the text more or less often than the kana for wa. And the so yeah, these are kanji statistics, right? Now I found kana statistics right here on the internet, and I copied them to save them. Let's try and open them. Third party here. Okay, doesn't know what browser to use or what to use to open it. Let's see if I can drag and drop here. Okay. Now this file does have some statistics here, and you can kind of from this you can gather the fact that E is the most common, and wa is not that uncommon. It's like about like maybe 2/5 as common as E, and so based on these numbers, I actually did some calculations, and it does appear that we would save work if we used wa here. And by the way, the calculations I did were based on the kind of like guideline that for readable kind of normal looking text, you have about 25% kanji and 75% kana. And this is, of course, an approximation, and not all text is like that. But based on some random sites, it seems like this is kind of like, if you don't know how much you like want to make your text readable, how much of kanji you want, you can aim for about 25%. If it's more than 25%, you start to get into this area where your text is correct, but it's a little bit like of a drag to read. So yeah, but the problem with these statistics, these kana statistics, are that they assume, or it was generated in a way that they took the kanji that were in the text that it was analyzing and converted it to kana. So it was it got they got like some books or some speeches, and they had some machine algorithm, some mechanical algorithm, convert the kanji to kana and then analyze that kana. But the thing is, that's not actually what we're doing. This makes sense if you're deciding like how to design a keyboard layout. So you want to know if do I have to, let's say if you want to type the word moji, right, for character, and here just converted it moji. So this means character, and you would type in those statistics were for input systems where you would type in mo for hiragana, and then ji for katakana for another hiragana, and then convert that with spacebar, right? But we're not doing that. We're doing direct to kanji input, and so we need to figure out what would happen if we're just typing the kana literally and we didn't have to type the kanji by means of kana. We're just we don't have that. And the reason why this is important is that certain characters here are probably not going to appear. They probably appear in kanji more often than they appear in as part of Chinese words more than Japanese words or Chinese origin Japanese words. So for example, wa, I'm very skeptical that this actually appears as kana very often, and I suspect that it's more like it appears in the pronunciation of some kanji that is very common, like watashi, which means me or I. So there's two ways to type that. There is watashi, there's phonetically, and then there is this way with kanji, right? So here we have two ways down here at the bottom of the screen. And now these probably appear like relatively 50-50, right? Like I don't think that either one is more common than the other by like any extreme amount. And so, but this is just an example. I assume that wa itself is more like it appears inside of like as the reading of a kanji, but not actually itself as a literal kana. And so, in order to analyze that, I'm going to write a tool which will just take some text and analyze how much each kana appears. And so that's not really going to be all that hard. I think I'll make a command like new sorts kana-stats, maybe something like that. We've been using underscore for separate words. So kana-stats, and then you give it some input like book.txt, something like that, and then and then we'll probably get like several books from an online database, and then just analyze that. So so there's a repository of like public domain books called Aozora Bunko, and let me see here. We can actually take a look at it. Go. Okay, this should work. Copy, and we will look at an example. So let's just say let's just look it up by author, I suppose. Here, just an author that I'm very familiar with, which is someone who writes mysteries and horror stories, Edogawa Rampo, which is supposed to sound like Edgar Allan Poe, but he's not really Edgar Allan Poe. He just likes him, so or named himself after him for his pen name for some reason. So let's just pick here. This is something I read before, and then we look. Let's see if we can get a text file. Okay, so this has Ruby, which means that it has the kana for every kanji. So this may not be the best example, but it doesn't have for every kanji, just the kanji that are hard to read. So this is probably good enough. The idea is we don't want to include kana, which are just readings of kanji. But so this one does include it, but generally it's not going to include it for every single word. So that's good enough. It's just going to include it for words that are kind of hard to read. So here, okay, doesn't know what encoding to use. So is there a way to tell what encoding to use here? I don't know what encode. So I don't know if the text editor probably defaults to UTF-8. But let's see here, more preferences, colors. Don't see an option for encoding. Let's save this and open it with something else. Or Chrome should be able to help me, right? Or a web browser in general. Let's get it here. Here we go. And then web browser. Okay, good. So yeah, it doesn't have Ruby for everything, obviously, but we can look for an example. Oh, here. So here's an example of where it's like showing you the kana for some hard to pronounce word. But I hope that it's not doing it like too often, because actually hakko, this is kind of a weird one to do it for, because it's not that hard to read. Ganjo. See, I'm wondering if it does it for every single occurrence. Himpan. See, I don't understand why you would put Ruby for this, but and tabako. This is kind of like done for maybe like elementary school children, it seems. Uh, but that doesn't really make sense. This isn't really appropriate for elementary schoolers as like a theme or as a story. Um, hmm. So what we'll probably do is we'll look for pieces of work that do not have that much Ruby in them or don't have any. Or we could also just automatically remove it, automatically remove these from the text, because the idea is we don't want to optimize the input system for like for inputting Ruby or inputting some kind of like specialized text, like maybe like classical poetry or something. We want to optimize it for colloquial stuff or kind of like everyday stuff. Not colloquial exactly. That's not exactly what I mean, but more like something that a normal person would write. So we wanted to figure out what encoding this was. Will it tell me? Page source. Oh, it's just a text file. It's not an HTML file. How do I figure out what the encoding is? History, more tools, tool settings. Let me take a break and figure this out. I'll just stop recording for a second. And okay, so it actually is written right here, the encoding. Shift JIS, which is not UTF-8 and is annoyingly different from UTF-8. But we can use iconv to convert it. So this is just Unix util, I think. So we want to use F to specify the encoding. So from shift JIS, I guess. And okay, that seems to be working. So we'll go desktop. Okay, that worked. Great. So that actually converted it to UTF-8. And so what we'll do is our tool that we write will not actually bother with encoding or anything. It will just assume UTF-8 and we'll convert it with iconv. So so that being said, we are going to need a utility before we start writing this other utility. So the problem is, let me get this out of the repository. This is go put this. Actually, we don't need to keep this because I already expanded the zip file. Let's remove it. Let me save this kana-statistics. Okay. All right. So yeah. Now at this point, we are going to write a tool which reads a file and kind of counts every single character that appears there that we're interested in, and those are going to be not every character in the file, but just kana. And these now we can limit the number of kana that we're interested in, and we can say like, oh, there's only about 100 different characters we care about, and so we can just create an array which is indexed by some kind of ID that we generate ourselves, and use that as the map of like character to count. Or we can just create a hash map which uses the real like string as the key, like the normal UTF-8 string as the key, and the value is the count. And so I'm not quite sure which way I want to go with this. The hash map is going to be generally, now there is no hash map in our code base, and I don't want to import any kind of other libraries for this. But at the same time, the hash map will be very generally useful in the future, and so I'm not quite sure exactly where I want to go with this. So this hash map doesn't need to support deletion, which makes things very easy. And we can also just kind of hard code the starting size, so that we just kind of like pick a starting size. Uh, we can, because we know how many entries there are going to be. I believe there's going to be about 200. I'm guessing. So there's like about 50 kana. Um, if you kind of consider the katakana and hiragana as the same character, there's going to be about 50. But each character, like K, so the character for ko, or ki, rather, ki can also have a small yo at the end for kyo. So um, we also kind of want to index this, I suppose, separately from this, because this is definitely going to be typed different from this, right? We're not gonna have like this be like four different keystrokes. We don't want to have a special keystroke just for small yo, because that only appears after a character that is like ki, chi, shi, or mi, or something like that, something that ends with e. And so it would be bad to have like a dedicated code just for yo. And so um, anyway, so because that is separate, because like ki is separate from kya, q, and kyo, that probably brings us to about 200, I think. Well, no, because there's about five different consonants, or maybe about six different consonants, and then you add kya, q, and kyo to each one. That's 18, so that's about 20 more. So that's like about 70 to 80 entries in the map, I believe. And oh, but there's also the dakten. So there's like so ka and ga are separate. Let's see, ka and ga, like that. Or let me not do katakana. Ka, ga. So you see the difference here is that there's like these. It's hard to see, but there are these two little slashes there. Here, let me type this somewhere else. Okay, so there's as you can see, ka and ga, and the difference is these two little slashes, extra slashes here, and there's also like ha and ba. And anyway, these two are separate, but I didn't include, when I said there are 50 like simple characters, that actually didn't include the Dakteng characters. So you're gonna have to add like another 30 there or something. So I think we're up to like 150, I'm guessing, and so the hash map will probably be about 200 or 300 slots, and then it doesn't have to support deletion, which makes it easy. And so we can actually just like have instead of have each bucket be a linked list in the hash map, we can just have each bucket be kind of flat. And so if there's a collision, we just put it in the next bucket. And so this ends up being a very, very simple data structure, all said and done. And so, yeah, I think that we're just about ready. There was other stuff I wanted to do. Maybe I should just talk about that so that I don't have it on my mind while we're doing this. But the other thing I wanted to do, if we look in romaji.c here, we have these things like these if-defs things. I actually want to make this parameterizable, and so that we can include this or exclude this like on a dynamic basis rather than having it be a compiler option. Because if it's a compiler option, that means that in order to if it's a C preprocessor option like this, that means testing it requires a complicated makefile. But if it's actually dynamically specifiable, that means we can use our existing test infrastructure to just test everything. So yes, I also want to make this kind of like customizable on a dynamic basis. That way, like later on when we're optimizing the input mapping, we can kind of like just flip switches and just see what works best. And that also other people can customize the system to how they like it. And at the same time, the existing tests, which use the old settings, will not have to be rewritten because we're just we can just run the test with different settings. So in other words, like turning this on could make the kanji mapping slightly different. Right now it's off. But if we turn this on, we don't have to rewrite all those tests which generated the kanji mapping, right? We don't really want to have to do that all over again. And so making it a dynamically configurable would be very wise, I believe. But that being said, we basically have to write a hash map, and I guess we'll test it as well. So separately from actually so we're gonna actually do this in a separate commit. We're gonna write a hash map, and so let's see how we want to do that. We have a util.h, which has these arrays and binary searches, and I kind of feel like it belongs here. So now we did arrays in such a way that we can use growable arrays rather, so that we tell the user, or the guy that uses the library creates a struct which looks like this. And what I'd like to do is make a hash map that kind of works very similarly. So we have that way we can use any type in the hash map without kind of requiring typecasting and unsafe cast and difficult to read code, because those casting can be confusing and hard to read. So we'll do like struct hash. This is an example, obviously. We have so you have type buckets. So each bucket will just have the how do we actually want to do this? So this is kind of tricky. So the bucket, will that have extra data besides the actual user type? We might have to have like a struct bucket type, which has like an unsigned, full. This is one. So this is like a bit that says whether or not it's actually set, but or whether or not the bucket is actually occupied. So yeah. I guess what we can do is we can just say if the data is totally zeroed out, that means the bucket is not occupied, obviously. But if it has at least one bit that's on, then that means it is occupied. And so we'll do something like a memcmp or something. There might be a better way to check if a bucket is, to see if a byte array is completely zeroed out already. So anyway, so we have type buckets, and we're going to have size t count. We don't really need a count, do we? I don't think we need that. So let's see. So we're not going to have to make type be a dynamically allocated object. It's just going to be like something of a constant size, because this is going to be predictable size. So we don't need like a memory-free operations or anything. So let's say we have like define free hash map, right? This is going to free the hash map. And we have, but the thing is, we also have the value. The hash key is separate from the value. So we're not really sure how. I'm not really. That's going to be another thing we have to consider. So we have size t alloc here, which tells us how much space is allocated for all how many buckets we actually have. So we can call like bucket count, I guess, or bucket count. But here we don't have count. We kind of have generic names for count and alloc. Maybe we just want to have a generic name here for consistency for now. But count sounds like it's actually the number of items, which we don't even care about. So we have bucket count. Let's call it bucket count. And do we need any other information here? I guess we need like function pointers that indicate like how to compare, how to calculate the hash values. Or we can just say like we just kind of we can just say the hash. We're just going to hash the bytes in a generic manner, like we just iterate over this and give you the hash that way. So here, when we do this, we can do like key type, and then we have a value type, vowels, and keys, vowels, and okay, so this is probably all we need for now. And we have a free hash map, we have a define, yeah, how do we want to handle this? So we do maybe like find key. Let's see. We need a way to insert as well as find something in the map. So yeah, how do we want to do that? So we can do like find hash map entry, I guess, and we give a hash map, and we give it a key, maybe like a pointer to a key, and then it spits out like a pointer, or it sets something to like a new key, new value. So it sets new key, new value as pointers to whatever you should insert it if you want to insert anything there. And yeah, so let's see here. Okay. Define find hash. So we also want to do I think that's all we need, right? I think that's all we actually really need here. Because once they do find hash map entry, they can check new key, new value, or like here, it's not new, it's more like found key and found value, right? And so they're going to set this will be set to the pointer that they're actually pointer to what they're actually looking for. And so this is like super primitive because this cannot be too large or too small. If key type is so it could be it's okay if it's too small, but the thing is you have to actually have all the relevant bytes to represent the key kind of inlined, or like not have pointers but actually have it all inlined. And at the same time, that means that you're going to have a lot of wasted space because you're going to have like blank you're going to have blank buckets, which are just all 0 bytes. And that's a little iffy. I'm not sure how much I like that. So maybe we actually need like a double pointer here, right? So, and here we have double pointer to vowels, right? And then that way, so it's an array, but it's an array to pointers, right? And so that way we can copy things in easily, and we know if something's actually there. So here we can do like define add hash map entry, I guess, hash. So that means I think we're going to need a separate find and a separate add function. So maybe it's okay to have these empty buckets though. How much do we really want to optimize this anyway? Is it okay? Let me think about this. I'm going to pause the recording for a second. Okay, so my thought is that we are going to have we're going to have a key, right? And we're going to have a value. Now the value is going to be 4 bytes, or 30, basically an int to which indicates the hiragana count of the character, and then 4 bytes for kana count, right? And for key, we have 3 bytes for first character, because this is UTF-8, 3 bytes second character, and 1 byte null terminator. Do we need a null terminator? Maybe we don't need a null terminator. So let's just say we have a null terminator. Now this adds up to 15 bytes, and we'll assume it's going to be 16 bytes in practice because of alignment issues. Now this is going to be better if we store it all like as a flat array, because if we actually have pointers to each key and value, if you think about it, the pointer itself will be 4 bytes, and the pointer will point to something that is 8 bytes, right? Each pointer will point to something that is 8 bytes, and each allocation will actually have like a size indicator at the beginning of it, which you don't actually have access to, but the system kind of keeps the size there. And so that's like extra memory, because you have the pointer as well as the size, which is stored for every allocated thing. So that's like an extra 8 bytes probably. Well, the pointer, I guess, itself is going to be 8 bytes, so that might actually be a lot. That might end up being 16 bytes just for the overhead of the pointer and everything, the pointer and the size. And so if you assume the hash map will have a 50% load, then it doesn't really help, because all the empty buckets will not really save enough space to justify having each occupied bucket be twice as large. And so I think this is going to make the API a whole lot simpler, right? So, because find hashmap entry will still it's just like find and free is all we need at this point. Because find is going to say, hey, if you want to insert it, you just put it here. So, I think we made that decision. So we can do like init hashmap, I guess, and we have hashmap, and we give it bucket count, right? So yeah, so let's see here. An init hashmap I think it should be able to tolerate either a totally zeroed out hashmap or a hashmap with like garbage data that was just allocated on the stack. Although maybe it would be safer if it checked to make sure it was zeroed out. That way it knows. Yeah, we can have init hashmap make sure it's zeroed out. I think that's fine. Okay, so we'll say like hashmap. So this is the example, something or other. Okay, we're going to write some documentation and init hashmap. So here we're going to just we're going to have to validate that it's actually empty, right? So we have do, so if we want to make sure that it's actually zeroed out, just for safety, we have so check if memory is 0. Let's see, because I think there might be a way to just check this kind of idiomatically. So here he's making a loop, memcmp. Okay, so here he's creating something to compare it against. And then here he's like saying, oh, you just need a test block. Okay. Starting leads. One. So I don't really want it to be efficient exactly. That's not totally necessary. Memory is all zeros. So this guy is using a loop, but a very fancy loop using C++. And here, okay, this guy is doing something even more esoteric. I don't know if that's necessary. Doing or equals instead of comparing to 0. I don't understand why that is faster. That doesn't sound faster. I'll give you a file array like this. BCP. Okay, so we'll just compare each field. So we'll say if hashmap dot keys or hashmap dot vals or hashmap dot bucket count, then we're going to make an error. We'll say, oh, we don't need a backslash here. So we'll do like bug memory not zeroed. And this way, this kind of makes it annoying because you have to, whenever you create the hash map, you have to set it to 0. But this is not that bad. You're just going to have to do this. And the benefit of that is that we can check for double allocation or like using a hash map without having freed it up. Right. So let's see here. Okay. So we're going to check if it's 0. So if not, now we're okay. So we can do hashmap dot bucket count equals. Oh, but we can't use the same name here. Otherwise, it's we'll just call it BC, I guess. BC. Okay, and then you do hashmap dot keys equals. What do we have? Xmalloc or XCmalloc? Forget what we did here. We have this special function to allocate a zeroed out array, xcalloc. Okay. xcalloc, and we give it the count first, which is going to be hashmap dot bucket count. Oh, we have to put this in parentheses here. And then count. Then we have the size, so we do size of hashmap dot keys, and the let's see, and count and size. That's all we need. Count and size. Okay. Now hashmap dot vals is the same deal, basically. Vals. Okay. And then you do while 0. Okay. So that's all we have to do to initialize it. And freeing it is also simple. Let's just do that next because we know it's easy. We'll do free. We have some function to free it as well as zero it out, I believe. Oh wait, we have oh yeah, we do have a bug macro. Good. Then where is that free? Yeah, free here. Okay. So we'll do free. Wait a second. Free is for arrays or it's for any allocated memory? It's for any allocated memory. And we have destroy array, which is separate. Okay. So we're going to free hashmap dot keys, free hashmap dot vals, and then hashmap dot bucket count is 0. Okay. So let's put this after free is defined. let's just put this at the very end. Okay, and we'll say like create a struct like this, and we're going to have to put the caveats that key type, bucket is considered, or key is considered absent if all bytes are 0. Right? Memory is not freed. Or like, key type and val type should be like inline structs. I don't know what the right way to say this is. Basically, it shouldn't be dynamically allocated. Or at least not dynamically allocated in a nested manner. So, and then, so comparison and hashing are done on raw bytes. Okay, hashing of the key. Raw bytes. Okay, good. So now find hashmap entry. This is going to be a lot of work. I mean, a non-trivial piece of code. So we don't. So what we want to do is we want to really delegate this to a function, right? We don't want to have to. And the way we do that is hashmap. So we're gonna have to get the keys. We're gonna basically pass the hashmap to a function, but like in a generic manner. So we'll do like find hashmap entry implementation. And this will take hashmap.keys. Oh, but we don't. Yeah, maybe find hashmap entry will just give you the index that you ought to use, right? So we'll say size t index, and that way find hashmap entry the macro will set these values here. So index equals find hashmap info keys and hashmap dot vals, and you also have to tell it the size of. Oh, let's do it this way. Map size of hashmap dot keys 0 spells, and size of hashmap dot val 0. Oh, and I also learned that you don't actually need to put parentheses around the size of. So maybe it's actually more readable to not do that. Size of hashmap.keyswing and size of hashmap.vals. Okay. So I don't think we need this do while wrapper if we are just calling. Oh no, we're going to have more than one line here. We do need it. So it's not going to work. Okay. Yeah, and there we go. And then bucket count. Hashmap dot bucket count. Okay. And yeah, so let's see here. What else do we want to do? Okay. I'm going to do while 0. Let's edit. Let's terminate it now. So now index is always going to be valid. There's no real reason why this wouldn't work. I mean, there's no error condition I can think of. If we assume the hash map is fully allocated, and we're also only going to compare like raw bytes, we're not going to like hash deeply. We're just going to do it shallowly. So we just are going to, I guess, do like hash map. Let's see. Then we do found key equals hashmap.keys plus index, right? That will give them the correct index to find something. found val. Let's call it. I don't know if I like the word vals. It's kind of awkward. I think we should just spell it out, to be honest. Vals, values. Okay. Keys, values. And then found value, right? Values. Okay. Now that's all we have to do. Now the problem though is that we let's see here. We didn't actually pass the thing that's being searched for to this function. So we will give it let's pass that as the first argument here. Say address of, or just key. Right. Well, this doesn't look all that good. Let's just make it the last argument. I can't think of a reason why not to do that. So so there we go. And this needs backslash, slash. Okay. So now the tricky part, I think, is implementing find hashmap entry impl. We need to find a decent hash algorithm, and I guess that's not really all that hard. It doesn't have to be a computation like a cryptographic hash. It just has to kind of do a decent job. We're only going to be using it for strings at first, right? So that's not really going to be all that hard, I guess. So I guess I can just write it now if I'm just going to use a kind of naive hashing approach anyway. That's just like multiply each number by, like multiply the hash by a prime number, then add it to then like add the next character, then multiply the hash by a prime number again, and then add the next character. It's just very straightforward. So okay, so we'll do size t, find hash map entry implementation, right? And so we give it void const keys. But that's not really exactly correct. Oh, yeah, that's fine. So we do void const keys and then size t key size, right? And then we have void const values and size t value size. Value size. And we give it a bucket count. And we give it a key to look for. So that will be yeah, I'm not sure how I want to handle this. Do I want to make this a, I guess, yeah, here. We'll automatically dereference it, or get the address of it. So we'll say void const target key. I guess that's a funny name, but okay. And yeah, then so that means that it's going to be onerous to I don't like having to deal with void pointers like this and adding sizes to it to find the size. That doesn't work that well in C. But yeah, so how about we do it this way? We'll say so instead of void, we'll say uint 8 type, right? But is that going to let me cast it without a? Is that going to let me convert it without a cast? I'm not totally sure. Let's just say void. Okay, then we're going to go to util.c, and we'll say we're going to start to implement this right now. Okay. Let's see here. So let's make sure this actually compiles. Return 0. Make, yeah. Uh-oh. Oh, we didn't put a semicolon here. Let's try again. Okay, that works. All right. So what we'll do is we will say, so first we need to find out what the hash of the key is. So we'll do like uint 8 score t target key pointer. No. Yeah, let's say target key. Or I guess I'll just do char. Char const. Okay, and pointer is redundant because the thing we're getting is a pointer, so we'll call it cursor. Suppose. Yeah, it's hard to think of a name when the name is already taken, isn't it? So let's just do this. Let's call it, or we'll just void. Call it void. Well, then it's kind of cryptic. The V is confusing. So let's just do an underscore here. Okay. I mean, for a reader of the signature, they're not going to know what the V means, so I'll rather not use it. Target key. Target key equals target key. Okay, then now we're going to have to hash this. So we'll do size t key hash equals 0. And we'll do size ti. Okay, we're going to make a for loop. So we'll do I is 0, I is less than key size, and I plus plus. Then we'll do key hash times equals 31. Key hash plus equals target key I. Okay, now we have the hash. Then we do key hash and bucket count, right? Now this is the correct index that it needs to be in. Or okay, instead of hash, we'll call it like bucket I. And oh, but we want to remember the start position, right? So let's call it key hash, and then we're going to loop through all the buckets and like look for a blank spot, the first blank spot after the key hash. So and how did we decide we wanted to check if it was equal to 0? I guess we're just going to use a check if an array of bytes is equal to 0. I guess we will just use a comparison, like just kind of compared naively. Yeah. Oh, yeah, because I didn't actually, and we didn't actually decide this yet. So the key size, we have to compare key size bytes to 0, right? So I guess we'll just use a for loop and iterate over the bytes. That's good enough. And so for, or we'll do like, here, do. We're going to do while loop, and we'll say or yeah, I wonder how I'm going to detect that we've actually looped over the entire array of buckets. Oops. Let's just start writing something. While 1. So if is zeroed, and we'll say keys plus keys plus, we're going to say I, right, we want to use I, don't we? Okay, so we'll say I equals bucket, or key hash, and we'll do keys plus I times, so in order to avoid a lot of multiplication, we're going to actually store the bucket count, or bucket total size equals bucket count times key size. Okay, and size t bytes processed equals 0. All right, and yes, so bucket total size. So we're gonna once bucket bytes processed equals bucket total size, then we know we've already checked every single possible bucket. So we'll do bytes processed plus equals per bucket total size, right? And now if, oh no, I mean we want to say key size. Now if key size is, or bytes processed equals bucket total size, then we'll say bug. Is it a bug or is it die? I'm not sure if we want bug or die here. I guess it's bug. It's not really the user's fault, right? So we'll say hash map is already full. Okay. So size t I equals, okay, so what we'll do is we'll actually say we need a void, or no, a uint or a char const key I, because we're going to basically look in key I for a valid spot. No, I don't think so actually. So okay, yeah, I'm thinking a lot in my head and not out loud right now. So let's my problem right now is that I'm trying to optimize early. I'm trying to figure out how I want to like detect certain problems and how I want to avoid too many multiplications. And that's just kind of like that's just a bad habit, I guess. So keys, let's get a keys pointer. So we do char const keys equals keys. All right, now we can index that more conveniently. So we'll do key size times I, right? Now zeroed, and we give it the size, key size. And if it's zeroed, then we just return. We're done. Return I. And we don't need any of that because we're either gonna die with a bug or return here inside the while loop. Now bytes processed plus equals key size, and so bucket size, and I don't know if this approach makes sense, this bytes process thing. So we is 0. Bytes are 0. Okay. And all right. Now, if it's 0, then we return that. We also want to just do this kind of thing. So let's just. We also want to compare it to the target key, right? So we'll say key found. So here. So let's save a pointer. So we're going to do char const bucket pointer equals this keys pointer. Bytes are 0. And we give it a bucket pointer. So now we do if mem cmp. We also want to compare it to what they're looking for, right? So we'll do target key and key size. Oh, we don't need to pass the values here to this function. Just realize that. Okay. And then bytes are 0, mem compare. How does this return? This returns 0. Oh wait, integer less than equal to again. For non-zero return value, size difference bytes. Huh. This is kind of complicated. Compares the first n bytes of the memory areas. The function returns an integer less than, equal to, or greater than 0 if the first n bytes of S1, is found respectively to be less than, to match, or to be greater than. Okay, so yeah, it's what you would expect. It's like string compare. So this is also going to return I. And okay. Then bucket pointer. So, all right. Then down here we want to do I plus plus, or I equals I plus 1, and then modulo bucket count, right? And so here we don't need bytes processed. We can just say if I equals key hash, then we have the problem, right? So now we don't need this anymore. We don't need this. And okay, I am going to take a break. It looks like I'm being interrupted now. So thank you for watching, and I hope to continue this again soon.